Welcome back to Java Internals Crashcasts. I'm Sheila, and today we're diving into the fascinating world of just-in-time compilation, or JIT for short. We're currently in our advanced topic season, exploring JVM internals. Victor, are you ready to unravel the mysteries of JIT compilation?
Absolutely, Sheila. I'm excited to discuss this crucial component of Java's performance. JIT compilation is a game-changer in how Java executes code efficiently.
Before we dive in, let's start with a quiz question for our listeners. Here's the question. In a typical Java application, what percentage of code do you think is actually compiled by the JIT compiler? Is it A, 100%, B, 50%, C, less than 1%, or D, around 10%? Think about it, and we'll reveal the answer at the end of the episode.
That's an intriguing question, Sheila. It really makes you think about how Java executes code. I'm curious to see what our listeners will guess. Without giving away the answer, I can say that this question touches on a fundamental aspect of JIT compilation strategy.
Absolutely, Victor. Now, before we get into the nitty-gritty of JIT compilation, could you explain what it is in simple terms?
Certainly. JIT compilation is a method of executing computer code that involves compilation during the execution of a program, at runtime rather than before execution. It's like a chef preparing meals as orders come in, rather than pre-cooking everything in advance.
That's a great analogy. So how does this differ from traditional compilation?
In traditional compilation, also known as ahead-of-time or AOT compilation, the entire program is compiled into machine code before it's run. Java, however, uses a two-step process. First, Java source code is compiled into bytecode, which is then either interpreted or compiled by the JIT compiler at runtime.
Interesting. So why doesn't Java just compile everything to machine code from the start?
Great question. There are several reasons. First, bytecode is platform independent, allowing Java to maintain its write once, run anywhere philosophy. Second, JIT compilation can make optimizations based on the actual runtime behavior of the program, which isn't possible with AOT compilation.
That makes sense. Can you walk us through how JIT compilation actually works in Java?
Certainly. When a Java program starts, the JVM begins by interpreting the bytecode. As it does this, it analyzes the code to detect hotspots, parts of the code that are executed frequently. Once a hotspot is identified, the JIT compiler kicks in and compiles that section of bytecode into native machine code.
Oh, I see. So not all code gets compiled, just the frequently used parts?
Exactly. This is a key optimization strategy. The JVM uses what's called tiered compilation to balance the trade-off between startup time and peak performance.
Tiered compilation sounds interesting. Can you elaborate on that?
Of course, tiered compilation in Java involves multiple levels of compilation. It starts with a quick, lightly optimized compilation for faster startup. As the code runs more, it may be recompiled with more aggressive optimizations. This way, the JVM can provide good performance for both short-running and long-running applications.
That's fascinating. What kind of optimizations does the JIT compiler perform?
The JIT compiler can perform a wide range of optimizations. Some common ones include inlining, which replaces a method call with the method's body, loop unrolling, which reduces the overhead of loop control, and dead code elimination, which removes code that doesn't affect the program's output.
Wow, that's impressive. Are there any downsides or challenges with JIT compilation?
Good question. While JIT compilation offers many benefits, it does have some challenges. One is the warm-up time. It takes a while for the JVM to identify hotspots and optimize them. Another is increased memory usage, as the JVM needs to store both bytecode and compiled native code.
I see. How does JIT compilation in Java compare to other languages or runtimes?
Java's JIT compilation is quite sophisticated, but it's not unique. JavaScript engines in modern browsers also use JIT compilation. The .NET runtime for C++ uses a similar approach. However, languages like C and C++ typically use AOT compilation, which provides faster startup times but misses out on runtime optimizations.
That's a great comparison. Now, I'm curious about best practices. Are there ways developers can help the JIT compiler do its job better?
Absolutely. One key practice is to write hot code, frequently executed code, in a way that's easy for the JIT to optimize. This often aligns with general good coding practices, keeping methods small and focused, avoiding excessive branching, and using appropriate data structures. Also, understanding how to use JVM flags to tune the JIT compiler can be valuable for performance-critical applications.
Those are great tips, Victor. Now, before we wrap up, let's reveal the answer to our quiz question. In a typical Java application, what percentage of code is actually compiled by the JIT compiler?
The answer might surprise many of our listeners. It's actually C, less than 1%. Most Java applications spend the majority of their time executing a small portion of their code, so the GT compiler focuses on optimizing these critical sections.
That's incredible. It really shows how targeted and efficient JIT compilation is. To summarize what we've learned today, JIT compilation is a dynamic optimization technique that compiles frequently executed code at runtime. It allows Java to balance between the platform independence of bytecode and the performance of native code. The tiered compilation approach helps optimize both startup time and peak performance.
Exactly, Sheila. And remember, while JIT compilation is a powerful tool, it's just one part of the complex ecosystem that makes up the Java virtual machine.
Thank you, Victor, for these insights into JIT compilation. In our next episode, we'll be exploring hotspot VM architecture, diving even deeper into the internals of the Java virtual machine. Don't forget to subscribe to Java Internals Crashcasts and leave us a rating if you enjoyed this episode. Until next time, happy coding.